In class activity 18E, Alice is standing on the ground watching a train go past her at 100 miles per hour relative to her position. On the train, Bob fires a laser, sending a photon of light forward at the speed of light, roughly 671 million miles per hour. How fast is the photon traveling relative to Alice? Well, based on the reading in preview assignment 18E, the speed of light should be the same for everyone. Therefore, relative to Alice, the photon is still traveling at the speed of light. But based on classical Newtonian mechanics, the speed of the photon relative to the observer on the platform is 100 miles per hour more than the speed of light. Then this contradicts Einstein's special relativity. Objectives for the activity: you will understand that rational functions are used in special relativity to correctly compute relative velocities. For speeds well below the speed of light, simple addition will suffice for computing relative velocities. You will be able to compute the relative velocity of an object under special relativity. Assume that the train Bob is moving on, assume that the train Bob is on is moving at a velocity of v miles per hour from Alice's perspective, and that Bob fires a projectile that is traveling with velocity w miles per hour from Bob's perspective. The classical formula for determining the velocity of the projectile from Alice's perspective is simply v plus w. The relativistic formula for determining the velocity of the projectile from Alice's perspective is v plus w over 1 plus v times w over c squared, where c is the speed of light. 2. Suppose Bob is on the train moving 20 miles per hour relative to Alice, and Bob fires a projectile moving 50 miles per hour relative to himself. Calculate the velocity of the particle. Let me move this up here. From Alice's perspective, using the classical and relativistic formulas. Well, the classical formula would just be the sum of the two. So we have 20, let me turn the pen on, 20 plus 50 gives us 70. Okay, and now for the relativistic view, we'd have v plus w, which is 20 plus 50, that's the numerator. And then we'd have 1 plus 20 times 50 all over 671,000,000 squared. Okay, so let's go to the calculator for this one here. That's a calculator. I have that entered in already, and there's that the relativistic fraction, and we get 70 as our answer. So back here, we get 70 as well. And is the difference in the formula significant? We'd have to say no. 3, if the train Bob is on is traveling at 400 million miles per hour from Alice's perspective, and he emits a particle traveling at 600 million miles per hour from his perspective, calculate the relative velocity using the classical and relativistic formulas. Again, is the difference in the formula significant? Well, if we add the 200 or the 2 together for the first part, we have 400 million miles per hour plus 600 million miles per hour. That gives us 1,000 million miles per hour for the classical view. Now, from the other view, the relativistic formula, let's see. Now, for the other view, let's see, I'm going over to the calculator. I have this entered in already, and you can see that we would get, let's count the decimal the places, we get 652 million miles per hour. So let's go back here and write 652 million miles per hour, and that is a significant difference. Part 4, we now consider the case of Bob on a train moving at 100 miles per hour, firing a photon at the speed of light. Part A, using the classical formula, how fast is the photon moving as seen by Alice? Does this contradict special relativity? Well, for part A, we'd have c, we're going to use c for the speed of light, plus 100 miles per hour And that's going to be faster. Excuse me. This is faster than the speed of light. So yes, this contradicts. Yes. That contradicts the fact that the speed of light is constant, so it contradicts. So for part B, using the relativistic formula, how fast is the photon moving as seen by Alice? Does this contradict special relativity? Well, this, let me just scroll this up a bit, is going to be 100 plus c for the speed of light, all over 1 plus 100 over c times c over c. We can write it like that. And this is going to equal to c, the speed of light. So this does not contradict the fact that the speed of light is constant. So there we go, not contradict. Part 5. Let me just scroll this all the way up here. In order to avoid using very large and very small numbers, we will measure all speeds as a percentage of the speed of light. Using these units, a stationary object will have velocity 0, an object moving at half the speed of light will have a velocity of 0.5, and an object moving at the speed of light will have velocity 1. In fact, in these units, c is equal to 1. Part A, assume that Bob is riding a train traveling at 1/2 the speed of light relative to Alice, so v is equal to 0.5. Bob emits a particle traveling at 3/4 the speed of light from his perspective, so w is equal to 0.75. How fast is the particle traveling from Alice's perspective? Let's see. So the velocity from the perspective of Alice is roughly, let's see, it's going to be v plus w over 1 plus v times w. So we get 0.5 plus 0.75 over 1 plus 0.5 times 0.75. And this is going to give us, when we calculate this, it's going to give us our answer roughly 0.91. So the velocity, okay, so the velocity is 91% the speed of light. Part B, assume that the train Bob is traveling on has a velocity of 3/4 the speed of light from Alice's perspective. Bob emits a particle traveling at 80% the speed of light from Alice's perspective. How fast is the particle traveling from Bob's perspective? Well, the velocity from the perspective of Bob can be found by solving the equation 0.75 plus w over 1 plus 0.75 w. And this works out to 0.80. Now, if we solve for w in this equation, the value of w is going to be just about 0.125. So the particle is traveling at roughly 12.5% the speed of light. There you go. That's the end of this video.